Hey there and welcome. I am absolutely thrilled you're here today because we are about to unlock one of the coolest, most fundamental secrets of how our universe actually works. Have you ever just stopped and wondered how things move? Or why certain objects seem to have this hidden power trapped inside them, just waiting to be unleashed? Well, today we are going to be talking all about mechanical energy. Think of me as your personal tutor for this explainer. We're going to break the whole shebang down together, step by step, making it super simple and honestly, a lot of fun. Because physics, it doesn't have to be intimidating at all. It's really just a way of explaining the everyday world around us. Okay, let's dive into this.
Here is our game plan for today. We'll start with number 1, what is mechanical energy? Then 2, the two types of energy. 3, energy at work, looking at hammers. 4, the math and energy formulas. And finally, 5, a quick pop quiz.
All right, let's jump right into section 1. What exactly is mechanical energy? You know, whenever we throw around big science terms, we're usually just describing things you interact with every single day. You actually already know how this works. Mechanical energy is, simply put, the ability to do work due to a body's position or motion. So the crucial point is that energy literally means having the ability to get work done. In science, work isn't a 9-to-5 job. It just means applying a force to something and making it move. Think about your daily chores. When you push open a heavy door, you are using energy to do work on that door. When a washing machine spins around to clean your clothes, well, that's mechanical energy getting a job done. It is all about motion, position, and having the sheer power to make things happen.
Moving right along to section 2, the two types of energy.
You are doing an excellent job so far. Now that we know what mechanical energy is in a broad sense, let's discover the two main types. This grand concept actually comes in two very simple flavors. First up is kinetic energy. This is the energy of motion. Basically, if something is moving, it's got kinetic energy. A rolling bowling ball, a speeding car down the highway, or even the spinning blades of a ceiling fan in your living room. These all possess kinetic energy because they are actively in motion. The second flavor is potential energy. This is stored energy, based entirely on an object's position. Imagine holding a heavy textbook high above your head. It's not moving yet, right? But because it's lifted up against gravity, it has the potential to do work if you drop it. Another great household example is stretching out a rubber band. While it's stretched out, it holds potential energy. Let it go, and snap, that stored energy turns right into motion. You are doing a fantastic job following along. You've basically mastered the two most important concepts in the whole lesson. Let's look at section 3, energy at work, specifically focusing on hammers. Let's keep this awesome momentum going. We're going to take these invisible concepts and see exactly how they accomplish physical tasks in the real world. Picture a common tool you might find in your garage, a hammer. When a carpenter swings a hammer, it becomes the absolute perfect example of mechanical energy in action. Let's look at the steps. Step 1, as the hammer swings down, it moves fast, meaning it possesses mechanical energy in the form of kinetic energy. Step 2, the moving hammer hits the nail, applying a really strong force. Step 3, that force causes the nail to be displaced, pushing it deep into the wood. And this brilliantly illustrates how we can harness energy to do work. The hammer's motion is transferred into a force that actually moves another object. It's just cause and effect, pure and simple. What happens with the hammer and the nail is actually part of a broader rule called collision mechanics. Whenever a fast-moving object hits a stationary object, whether it's a hammer hitting a nail, a baseball bat whacking a ball, or even your foot kicking a soccer ball across the field, mechanical energy is being harnessed to apply a force. The result? The stationary object is forced to move in the exact direction of that exerted force. That is the very definition of doing work. Literally, every time you push a chair across the kitchen floor or slide a book across your desk, you're demonstrating this exact principle. You're transferring your energy into the object to displace it. Let's hit section 4, the math and energy formulas. Okay, take a deep breath. I know, sometimes math can seem a little tricky or intimidating, but I promise you, in physics, formulas are just a super convenient shorthand way to write down exactly what we've already been talking about. You already understand the concepts, so this math is going to be a breeze for you. Let's look at the big picture first. The total mechanical energy of any system is just the sum of its potential energy and its kinetic energy. That's literally it. Total energy equals potential plus kinetic. It's just adding together the stored energy of an object's position and the active energy of its motion. If you have both, you just add them up to find out the total ability that object has to do work.
Let's move to and see how this builds our specific formulas. Here's the formula for potential energy. P E equals m times g times h. Let's break those letters down. The m stands for mass, how heavy the object is. The g stands for gravity, which is a constant pulling force we have right here on Earth. And the h stands for height. So if you want to know how much stored energy an object has, you just multiply its mass, the pull of gravity, and how high it's lifted off the ground. The heavier the object and the higher you lift it, the more potential energy it stores. Make sense? And here is our formula for kinetic energy, the energy of motion. Ke equals 1/2 times mass times velocity squared. Again, mass is just how heavy the object is. Velocity just means speed, how fast it's going. You square the speed, multiply it by the mass, and cut it in half. Notice that velocity is squared there. That means the faster an object moves, its kinetic energy increases massively. And just like that, you've conquered the math equations for this lesson. Seriously, give yourself a pat on the back. You are doing an incredible job.
And finally, Section 5, pop quiz time. Let's test your knowledge.
All right, we have reached the final section of our explainer today. Don't worry, there are 0 grades here. This is just a fun, low-pressure checkpoint for us to review and solidify everything we just learned together. Are you ready? Let's do it. Here is your question. If an object, let's say our really heavy bowling ball, is lifted high above the ground and just held up there, what kind of energy does it possess? Take a second to think about it. Is it kinetic or is it potential? I know you know this one. And the answer is potential energy. Now, what's really interesting about this is how it perfectly captures that idea of stored power. Because the object is lifted high up, gravity desperately wants to pull it down. It has the potential to do a ton of work the literal second you let go, all thanks to its position. If you got that right, awesome job. If not, no worries at all. That is exactly why we practice these things. To wrap up our time together, I want to leave you with this core truth right from our lesson. Mechanical energy is the ability to do work. Whether something is flying through the air with kinetic energy or waiting up high with potential energy, it holds the power to change the physical world around it. You've done an amazing job exploring this with me today. Before you go, I want you to look around the room you're sitting in right now. What hidden forces and stationary objects around you have the potential to do work? Keep questioning, keep exploring, and I'll see you next time.